Hello friends, thank you very much for watching again. Here is lesson 48 already from the Java Fundamentals stream, and we are going to discuss further about threads. We had already a couple of lessons on this subject and we continue our discussion today. In the previous lesson we discussed about synchronization. Today I will continue on that example to teach you how the wait and notify methods work, and then we'll discuss about the volatile keyword. Maybe we'll even touch the deadlock subject, which is one of the common problems that appear in multi-thread architectures. So this is basically what I've planned for this lesson. And with that being covered, then we'll be able basically in the next lesson to go directly to executor services and to already start discussing the more high-level frameworks that you can use in terms of multi-threading with Java, like the executor services. They will be first, and then we'll discuss about the fork join framework, and then about parallel streams and so on. We have a lot of subjects actually to discuss on this topic. So thank you Ben again for being here with me, and if you're watching the event live, don't forget that you have a live chat there, so I always have an eye on the live chat. If you're watching the event recorded, then you can still ask questions in the comment section, or you can find me on Twitter or on LinkedIn and you can ask me questions there as well. And I will try to answer them in a separate video maybe, or in one of the next lessons depending on your questions. So let's go directly to my computer and I will try to show you now how things work in terms of synchronization together with wait and notify. But first of all, I want to make you aware that I have copy-pasted the previous example we worked on together in the previous lesson. So in lesson 47, I have just renamed this example in example for lesson 48, and I have added here a -1 as well, because I expect that I will have to create a separate example for my next, a separate project for my next example. But it's basically precisely what you have seen developed from scratch in the previous lesson, so I won't retake redeveloping it. You already have seen how to develop this code from zero, and I will use it now to show you how notify and wait works. Before going to the subject, into the new subject regarding the notify and wait, I'd like first to go together again through all the code to make sure that you remember how the application we developed together in the previous lesson works. And then in the previous lesson I tried to use an analogy like the police officer and the intersection analogy for the synchronized keyword, and to teach you how synchronization works. In this lesson I will try to use some visuals, and again just to make sure that I use all the possible tools that I can use to make you understand easier this topic, which is a very difficult one, of course, because as I've said multiple times already in the previous lessons as well, the multi-threading and this part of using threads in any programming language and on any platform is probably one of the most difficult subjects that you can touch in software development. So what we had actually, if you remember, so we had this producer-consumer architecture where the producer and the consumer classes designed two different threads. Of course, then we have actually implemented multiple instances of the same kind of thread. In my case, I have implemented two producers and two consumers here. Well, the producer is designed in the producer Java class. You can see it here. And you know that's basically running continuously. You see here this while true, so it never stops. It only stops when you actually stop the application, and it tries to add values, just random values, to a list that we have instantiated here in the main class. So it's a unique instance. You see that the variable is declared static, which makes it unique in the class, and that's why we call this resource a shared resource of the same of all the threads of the application. And that's why basically what we confront here is a race condition problem, for which we had to use synchronized blocks to make sure that whenever somebody works with the list is only one thread at a time, which will be either a producer or a consumer at a time. You cannot have, in our case here, two threads at a time trying to access the same resource, which is the list we have called the bucket, in which we throw random numbers and from which the consumer takes out those numbers and prints them out in the console. So that was basically the whole architecture. Again, if you didn't see this in detail and you want to see it in detail, it's just the previous lesson named 47, and which you can of course find it here on the same channel. So I will now try to continue what we already discussed. So if you didn't see the previous lesson, then my recommendation is for you to first see that lesson and then come back to this one. Otherwise it might be more difficult for you to understand what we are discussing here now. So again, going into one of my favorite tools for the drawing visuals here, let's remember what's basically our application doing. So I actually have, let's say here, this rectangle is one of the synchronized blocks, and I will say that this is basically the synchronized block of the consumer. So this is the consumer itself, and the block is the synchronized block of the consumer. I might want to actually write synchronized here to make sure. Synchronized. Okay, so we have, in our case, in our application, we have two synchronized blocks, and one of them is the synchronized block of the consumer and the other one is the synchronized block of the producer. So we might of course now have multiple instances of consumers and producers, and like in our case, for example, we have two consumers, two instances of consumers that we have created in the end, and two instances of producers. And of course you can have as many producers and as many consumers as you'd like, so you can have even more than this, but for us a couple of each of them was basically enough to make our demonstration. So now what happens, and let's now rename this. This is C1 and this is C2 and this is P1 and this is P2, and this in my visual here, these are basically precisely the instances that you have created here in this example. So we have created two producers, two consumers, and the representation of the rectangle is the synchronized block from each of the instance, which is in our case, going back, the producer has synchronized the decisional structure here, where we work with the bucket, where we actually change the bucket by adding new values to the bucket, and the consumer as well has a synchronized block. This is the rectangle in my visual, which synchronizes the decisional structure here that again works with the bucket. And the reason we've added these synchronized blocks is because we work with a shared resource, and as we've discussed in the previous lesson, when you have multiple threads working with the same resource, which is called the shared resource because they share the resource, then you have to synchronize it. Otherwise, you will face problems when the two different threads will actually try to change the same resource. And that's called race condition, and that's basically again the thing that we discussed in the previous lesson, and for which we've added synchronized. We've actually even started from developing this application, let's say, in a wrong fashion. We've developed it without synchronizing it, and then I've started the application. You've seen that's crashing, and then we've corrected the implementation by adding the synchronized blocks. So what actually happens with this synchronized here, let's just take a look with my visual here, is that when C1 manages to obtain the access to the synchronized block, so access to the lock, and what happens here is that we have a monitor. Remember, the monitor is that object we use to manage the synchronized blocks. So without the monitor, you have no possibility to know who is actually getting the lock. And the reason we have actually decided to use as a monitor the list itself, which in our case is called the bucket. So the bucket is our monitor here, and this is like a police officer taking care that each thread will enter the intersection at a time. They will not be at the same time two threads inside the intersection. So what happens here now is that, say C1 manages to obtain the lock for the bucket, that actually means that here now C1 it's actually working, and it can work with the synchronized block. So unless now C1 will basically release the lock, that means C1 will end working, will finish the synchronized block. In our case, that means we entered the block, so we've passed this curly brace here. Unless it ends the block, or you will see now somehow it gets into the blocked state. In this case, no other thread can actually work, so that means that you will see no other red bubble here. So that's not possible to have. For example, it's not possible to have two red bubbles. It's not possible to have two different threads simultaneously in a synchronized block in our case. So it will be either one of them at a time, which means that when this one finishes, this will go here or here or here. So it will be one of the threads at a time managing the its synchronized block. And the reason it's one at a time is because the same monitor, which is the bucket, is managing all of them. If you would have had two different monitors, say for example you would have had a monitor called M1 for the consumers and another monitor called M2 for the producers, then what you would have had? You would have had a possibility to have the producers and the consumers independently managed, which means that a consumer at a time could have acted into its synchronized block and the producer at a time could have acted in its synchronized block. So that would have mean to change our implementation, and instead of having only one monitor, having two of the monitors. So in this case, basically that would mean this bubble here will go from here to here. So one of the consumers at a time, one of the producers at a time, because we have one monitor managing these two, one monitor managing these two. And of course, assuming you would have had one monitor for each of them, so that would be, for example, if you would have used this instance, so each instance itself as a monitor, then in this case you would have actually had 4 monitors, isn't it? So that actually means in this case that you can have multiple at a time, so each monitor is actually designed here. So yeah, in our case it's only one monitor. In our case it's only one, it's only the bucket. You can see here that the synchronized block uses the bucket, as well as here this synchronized block as well uses the bucket. So this means that we actually use one monitor for all the instances. So that means in our case it's only one block at a time executing. So the red bubble there, it means the block is executing. So what you can have now in our case, where we only have one monitor, which is the bucket, then it's only one of them. But I wanted to with this visual to make it a little bit clear, because I know that in the previous lesson you had some problems understanding this monitor and the way it works. So now I hope it's a little bit more clear. And anyway, if it still isn't, but it's a little bit at least more clear, but it isn't crystal clear yet, no worries, this comes with experience. So while we will be working with more and more examples, I'm sure you will get more understanding on this monitor and the way it works. So yes, the reason we use only one monitor, which in our case is the bucket, is because we really want only one of these threads to actually be active in a synchronized block at a time, because we want to make sure that only one thread at a time can change the bucket. Otherwise, because the bucket itself is an array list in our case, which is a non-concurrent collection, if you would have multiple threads trying to change it at the same time, we get into those problems we faced in the previous lesson. So yes, this is basically it. So now I hope this is more clear. We still have kind of a problem with our implementation. We didn't discuss it in the previous lesson because there was no more time to cover this topic, and that's why I'm continuing it now. And it's not a functional problem actually, but it's rather more a performance problem, an edge case that we don't cover in our implementation. And that is what actually happens if the condition here, either for the producer or the consumer, is false. So okay, we have focused on what happens if the condition is true. We know if the condition is true, well, we actually in case of the consumer, we are going to consume one of the values in the bucket. Because if the condition is true, it means that the bucket isn't empty. If it isn't empty, it means that it has at least one value. So then we can go further and consume that one of the values. It can be the only one or one of the multiple values you have there. But what happens on the other side when this condition is false? So in our case here, because we are on the consumer, the condition being false would mean that the bucket is empty. So what does actually happen if the bucket is empty? So it turns out that if the bucket is empty, we are here inside a while loop. And that means that, well, it can be that the same thread will be executing the condition again and again and again, or another consumer in our case. So say that it actually happens that this is false. Going back to our visual here, it means simply that you don't know the JVM how long will actually stay with this thread available. So actually imagine that the JVM will make this thread available 5 seconds. It's a long time, but I've just used this time because it's easier to imagine. Say C1 will be executed for 5 seconds. So can you imagine in 5 seconds how many times would the consumer execute this condition? Of course, the answer is a lot of times. We don't know, but it's a lot of times. If you keep the same thread for 5 seconds executing this condition, would it make any sense? Well, not really, because if the condition is false, which means that the bucket is empty, and you leave the consumer retesting the same condition, will ever the bucket have at least a value? No, because the consumer doesn't add values. The consumer will only test that that the bucket is empty, but because we are inside the synchronized block here, and there is no other thread at the same time, because we discussed we have only one monitor, so it's only one thread at a time executing, which is our consumer. Basically, there is no producer now to add a value. So the condition will never change. If the consumer simply stays 5 seconds there and it simply tests the condition again and again and again, it's no chance that the condition will get true at a specific time. So in the case of having our condition false, well, it's the case of having the condition false here, we simply, the way we've implemented it, we simply let at the JVM decision how many times would it like to let the consumer execute this condition, which is of course not performant, because we already know that if the condition is false, then from our perspective, that consumer should automatically somehow get out and leave a producer enter the stage to add at least a value for another consumer then to be able to consume something. Because if you don't have a producer to add a value, you don't have a consumer. Any consumer cannot consume anything, and that condition will stay forever. Will stay forever, not really forever, but will stay while the consumer is active. Will stay false, and then only when the JVM decides to add a producer on the stage, then it will actually add values. And if you take a look on the other side, on the producer side, it's basically the same problem, but it's just just on the other edge. Is like when the list has 100 elements. So when you have the list already with 100 elements, then this condition will become, of course, false. And then if the producer tests the condition again and again and again without having any consumer on the stage to actually get out a value from there and make the size of the bucket being smaller than 100, then the only thing that happens here is that the producer will basically test 1,000, 2,000, a million times this condition, which will always, of course, be false. It can't get through unless a consumer gets out a value from the list so that the size becomes smaller than 100. So this is our problem. It's basically, again, not a problem in terms of the functionality itself. So our code is working correctly. It's just that it's less performant when it gets to 0 or to 100, when the list either gets full or it contains no elements. We can get into a situation in which a lot of resources are spared without any sense. So how can we change this behavior? How can we implement something such that when this condition is false, we make our thread wait? So we want to, the logic is like this one. If a producer finds out that there are already 100 elements and it cannot add one more element to the list, then instead of remaining there continuously testing the same condition, which will never ever get through if no consumer gets into the stage, instead of that, we'll actually have to wait to leave another thread go into the stage. And fortunately, at some point, either a consumer will enter the stage and then it will make the list again with a size smaller than 100, or in the end all the producers will actually wait and then still a consumer will get into the stage because the JVM will have no other option. So we'll have no other thread to actually add into the running stage. So to do that, we actually have an option. Of course, in our case, it's easy to know when to add it. The condition will be on the else side. So that means when this condition is false and the producer cannot anymore add values, it has to wait. And it is, guess who? It's the monitor who is managing the thread, telling the thread to actually wait. Well, you see, wait is one of those methods that puts the current thread to the state blocked. And if you remember, we have discussed a couple of lessons ago that all these methods, in generally all these methods that block a thread, also throw an exception, a checked exception named interrupted exception. You can see it here. So the reason you see wait being underlined with red here, which signifies a compilation error, is because indeed by adding wait, we now have this interrupted exception, and we have to add a try catch for it. Otherwise, being a checked exception, our code cannot compile. And remember the interrupted exception, and that's a good thing to remember, especially for OCP 11 and OCP exam in general, is that almost, let's say, you can take it any method that blocks a thread throws interrupted exception. And we have already seen sleep, join, if I remember correctly, with work with join, and wait now is the third method of this kind we discuss about. So remember, all methods that block a thread usually also throw interrupted exception, and that's a good thing to remember for your OCP exam, because, well, you'll easier remember when you have an exception and the code doesn't compile. So now to make our code compile, of course, I have just surrounded everything with a try catch. So interrupted exception is my exception, and now basically everything is fine again. So what have I done here again? I've told my producer that if there are if the list is full already and it cannot add any more values, then it has to wait. Then this is the line where the producer waits now because it cannot anyway add any value. And with this line, what we've managed to do with this line is that we have made our producer wait for a consumer to consume a value before it tests again the condition. Otherwise, without that wait there, our producer would continuously run the evaluation of the condition, which it doesn't make sense because we already know that this condition won't become true if one consumer wouldn't consume a value, isn't it? So that's basically what we want to do. Producer, okay, that's fine. So now, why do we call the wait method from the bucket? That's the next question you probably have now. Why didn't I say this wait? Is that the same thing? Well, it turns out no, it isn't the same thing. Always when calling wait and notify, this pair of methods we discussed now, these are methods that you always have to call only inside the synchronized block. Never ever call such a method outside a synchronized block. It doesn't make sense. Wait and notify are two methods you can only call when you are inside the synchronized block. That's the first thing you need to know. The second thing you need to know is that it is always the monitor, that object from which you have to call wait and notify. You cannot call wait and notify just for any kind of random object. It always have to be the same object that you use as the monitor of the synchronized block, because the logic of it, and now I'm going back to that analogy from the previous lesson with the police officer. So being you have an intersection with cars and the police officer in the intersection managing the cars, who is the one able to tell the cars to stop or to enter the intersection? Just think about the intersection, leave completely behind the code. Just think about the example with the intersection. You have one intersection, one crossroads, and you have a police officer in the intersection, and you have cars. Who has the responsibility to stop the cars or let them in the intersection? It's the police officer, of course, which is basically our monitor. Because as you remember from the previous lesson, we have compared the synchronized block with that square of the intersection, and we have compared the monitor with the police officer, which has the authority to, in our case, to tell the threads to enter the synchronized block or stop and allow the other thread inside to finish. And that's basically very, very similar to how a police officer inside an intersection allow a car to pass and can also tell other cars to, of course, wait. So it can tell them, okay, you now wait, as the police officer always saying that. So that's why wait and notify, first of all, first rule of thumb, you cannot use them outside of the synchronized block, because these two notions only make sense inside the synchronized block. And you always call them from the monitor of the synchronized block. If you don't do that, you will get an exception, because again, the logic of wait and notify is the logic of having a monitor being able to manage the threads. And wait and notify are methods that you can use to manage your threads inside the synchronized block. And basically what you can do is to stop the threads using wait, or to, as you will see further, leave them go by using the next method, notify, we will also use in the same example. So I hope this analogy with the police officer is clear, and you now understand why wait and notify can only be inside a synchronized block. Before going further with my implementation, because of course I've just now, for the moment, I've just made my thread wait, but maybe you think already that I need at some point to also make it go again, otherwise it will stay blocked forever. So you have to tell a thread stop, and then you want to tell at some point the same thread now you can continue. Otherwise, if you don't tell the thread that it can continue, it will wait forever, and you don't want that, because now I've blocked completely my thread. So now what I want first to tell you one more thing before continuing is that wait and notify are part of the class object. That's an interesting thing. And the reason for why these methods were designed, as you can see, in the object class, which is a very important class in Java. It has a very strong significance. This object class is the root of the inheritance tree of classes in Java. Everything in Java extends object. When you don't extend object, it automatically extends object. Remember this rule we discussed in earlier in the stream when we were discussing the object-oriented things and I don't know, the inheritance and so on. We discussed at some point also about the object class, and you know that the object class is a very special class in Java, because any object is extending the object class. So that actually means that all the objects get the methods from the object class. So that actually means that wait, together with notify and notify all, so the other two methods we'll discuss, there are three methods, they are part of any object. And the reason they are part of any object is because you actually can use any object as a monitor. So in Java you can actually take any kind of instance, any object instance, and use it as a monitor. And that's why wait, notify, and notify all, so these methods are directly up there in the object class, and they are inherited by absolutely all the objects in Java. So you can basically use the wait and notify from any object in Java. So now I've told my producer that it has to wait. The next thing, logically, is to tell my producer to continue. And when would the producer want to continue? Where in our case, our producer entered the block state because the list already had enough elements and the producer couldn't add more elements. Logically, it might continue only after at least one consumer consumed a value. Because say one consumer was executing and it actually consumed the value, now you have less than 100 values in the list, and then it makes sense that the producer can continue its execution. And where is that? We're basically in the consumer class. So now I go in the consumer class, and immediately after removing a value, I will notify my thread. So I will basically notify the thread to continue, and I have two options: the notify method and the notify all method. The notify method will notify only the next thread that's waiting. The notify all method, as the name suggests, will notify all the waiting threads. Because in our case, we don't know if the next thread will be a consumer or a producer, and we have no option to know that. In some architectures, it makes sense that you call notify, but in our architecture, you don't know which one is the next thread. The only option, the only logical option here is to simply call notify all. And if one of the threads that will be called here will be entering a state where the condition is false, it will go to a wait state again. So that's it. But yeah, in our case, the most logical thing to do is just notify all the threads. I will try again to represent them then also visually, so it maybe it's more clear. But anyway, what we've done now is we made the producer wait when it cannot add any values, and when at least a value is consumed and it makes sense that the producer can continue, then we notified all the threads that are waiting, so including our producers, and that means that our producers can continue now. And basically the same thing now you can do to the consumer. So when the consumer waits because there are no values, what you need to do is to make the consumer wait. How do you make the consumer wait? Well, basically in the same way we made the producer wait. You use the monitor, you call the wait method, and now of course we need to add a try catch for the interrupted exception. And then when it makes sense that the consumer should continue, well, the consumer should continue when there is at least one value in the bucket. That means when one producer has added a value. So the same thing, like a mirror, you notify all the threads when a value has been added, which means I notify all the consumers out there when the value has been, when a new value has been added. So with this, we basically covered the edge case, because at the moment, I won't run the application again because you know that my computer will get stuck and then I will have problems with the streaming. But and anyway, you can't observe this. It's very difficult to observe the result. But you can imagine now that at least by adding these instructions, we simply make sure that a thread doesn't run the same condition a million times without sense. It's simply when a producer will find out that it cannot add a value because the list is already full, it will wait, and it will basically wait until a consumer will notify it. And the same way around, when a consumer finds out it cannot consume values because the list is empty, it will wait, and then it will be notified to continue only when a producer, only after a producer has added a new value. So that's how you use the wait and the notify. Wait is used to put into the block state the current thread, and then you can use notify to notify to allow that threads that are waiting to continue. So that's basically how you use wait and notify. And visually representing this, it's basically what happens is that, say C1 enters this list, enter this block of this synchronized block, and this is my list, okay, which is empty. So I have a question: if multiple threads are waiting, when notify is called, how do they know which thread is the next one? Where's the JVM? That's why I basically use notify all, because you don't know which is the next thread. And because I have the possibility that I have also other producers waiting there, what I wanted to, or what I thought is better to do here is simply to call notify all. When you call notify, is the decision of the JVM which is the next thread that will be notified. When you call notify all, then you simply notify all the threads. So that's the difference. I hope this clarifies the difference between notify and notify all. So what happens here, say our list is empty. You see it's empty now. So I have the consumer here that gets the execution. It tests that the list is empty, and because the list is empty, now the thread actually gets blocked. And I will mark it with a blue, like this. So it's blocked. And because the thread is blocked now, and it's blocked because it entered the wait, it called the wait method, the monitor called the wait method, so it blocked this thread. Now, basically what happens is that the JVM has to choose one other thread. So there are multiple options. It can be P1, it can be P2, or it can be C2. Well, in the happy situations, a situation in which the next thread called is P1, and that means here it should be a red because it's executing. Red, it means it's executing for me. Okay. So in this case, what happens is now the producer that's executing entered the synchronized. Mind that it can enter the synchronized because there's no active thread in any of the synchronized. So the synchronized block allows, in this case, P1 to execute, because there is no other active thread. This one is blocked, so it's not seen by the JVM. So it's like it's empty, even if we know at some point it took the lock. So what happens here now is that, again, P1 is the next thread. It will generate a value, I don't know, say 10. And immediately after adding a value into our list, of course, P1 can execute further and add more values. For simplicity, let's assume it doesn't. Next thing after adding at least one value anyway, because when it adds at least one value, it notifies all the threads that are waiting, which means in our case that this one here now becomes, actually it becomes runnable, not necessarily read, but being runnable, then it can be taken by the JVM and put into execution. So it simply, we should have been actually deleted it. That means it's not blue anymore, it's not blocked, so now the JVM can choose C1 again and put it into execution. The other thing that could happen, again, say the list is empty, the consumer C1 is executing, it finds out the list is empty, it gets blocked, and again we are in the situation in which the JVM can choose out of P1, P2 or C2. Of course it can choose P2, which will lead us to the same scenario like in my explanation, but it can also be that it chooses C2. If it chooses C2, then this consumer as well will see that the list is empty, which means that it will automatically get blocked as well. So at some point, blocked was in my case with blue, isn't it? So it gets blocked. This one as well as this one, they are blocked now. So it can happen, this can happen at most up to all consumers. Say you have 10, all 10 will be blocked at some point. Like we have now 2, both of them are blocked. And now the JVM has no other option. The only option it has is to add one of the producers. Okay, so the only option is that one of the producers will become active now, because it doesn't have any other option. And now when this producer adds a value to the list, then it says notify. If it says notify and not notify all, only notify, one of these that are waiting will become active. If it says notify all, then both of them will become active again, and everything starts again. So that's the whole dance of the consumers and the producers using notify and notify all. So I hope my explanation was clear enough to make you understand how notify all, notify and wait methods work and how can you use them. So when you'd like to actually make one of your threads wait and then make them in a specific condition continue at a later time, you can use notify, you can use wait and notify for this matter. But remember, always inside the synchronized block. You can't do it otherwise. So now, that being said, I would like to create a second project. And the second project is the one I will use to describe you how volatile works. And this is another keyword related to multi-threaded scenarios. Of course, it's an important word that you might want to use even in real world scenarios if you get implementing specific multi-thread architectures. But of course, it's more possible than in the near future you'd actually encounter them in the OCP exams. Link is not in the description because I didn't commit, sorry for that, but I can commit my code only after I write it. So yes, link is not in the description, but it will be in the description after I finish. So whenever I do finish a video, I do add the link in the description and in the comments. I need first to write the code and then I commit it so that you have it. I cannot just have the link before before committing the project. That's why you don't find it in the description. But yeah, once I finish the video, you will have the code, you will have the link in the description as well. Okay, so now basically we are going to create a second project. I will call it Java Fundamentals E48, and this is the second one. And I can actually close the first one because I want to spare my resources. Okay. Yes, previous 47 projects are there on in the comments for each of the projects. You can find them already. So the only one that misses is the one that I have in progress. Okay, say I create here a main, and what I want to do is basically I want again to have a shared resource. So I will create a main class, and I will again write something like public static. It can be a simple object somewhere as well, but to make my life easier here, I think a static would be a easier choice. And I have a C starting from 0, say, and then I have two kinds of threads, the incrementing thread and then the decrementing thread. So again I say incrementing thread, which extends thread, and what basically this thread does is simply incrementing the value of x, of C, sorry, in my case it's not x, it's C, which is basically not something something very strange, but you can say, let's say even we have some sleep here, and it does that for every 500 milliseconds. That's its whole purpose. So it's a very simplified thread that is changing a resource that can be accessed by other threads as well. So I have to treat interrupted exception again in this case because it's a checked exception. Okay, and then I have a decrementing, no, not a decrementing, I have in this case, sorry, not an incrementing thread and a print thread. I want the second thread just to access the resource. I don't want to change the resource. So let's say printing thread. So the printing thread extends thread and then once at a time is basically, I forgot here to add my while true. So my idea was to actually, this should happen continuously, or if you don't want a while true, you can actually do it for or something a few times. So let's say the same thing. So I print it out and I print main C. Okay, so in case of such a code, and yeah, let's make it thread sleep again. So what we can expect in case of such a code that I have written here, if I do start two threads at the same time, one which is incrementing and the other one that's printing, I think it's pretty clear from here that one of the threads, the incrementing thread, is the one incrementing the value, so changing the value of C being here this variable, and the printing thread will actually be the one printing out the value. So now the question is, and again this is something that you can't really prove by running the code, but I wanted to make sure that I write the code so that it's better that you see also the code to understand better what I want to do here. Now you have two threads here. So one of the threads that's called the incrementing thread, and the second thread, which is called the printing thread. And then we have a value somewhere in the memory, which is C, and which initially has the value 0. So now say that the incrementing thread here is running 10 times. So this running 10 times, that means it runs the while for 10 iterations. So what does it actually happen if the incrementing thread executes this while for 10 iterations? Well, C will become first 1, then 2, then 3, and then up to 10. So theoretically, if this incrementing thread runs its while for 10 iterations, then what we do expect is that the value here becomes 10, because it did 10 incrementations, plus 1, plus 1, plus 1, up to 10. And then say that after these 10 incrementations, the printing thread will print the value in the console. The question is, what is the value that will be printed out here by this printing thread after 10 iterations executed by the incrementing thread? And you will be tempted to say it's 10, isn't it? Because, yeah, why not? We have C that's 10, so C will be printed out and C becomes 10. Why? It's not that, isn't that logical? And it turns out that it's not in all the situations. It might be or it might be not. So it might actually happen that this incrementing thread will actually simply increment the value 10 times, but the printing thread might actually print 0 or a different value. So now the question comes, how can that actually happen? Because it doesn't really make sense, isn't it? I mean, we have only one variable C that you increment, and then do you say that when we print it, it can be a different value like 0? How is that possible? Well, it is possible, because what happens is that it's not guaranteed the value 10 here of C is stored in the main memory. So this is what I've printed here is basically the main memory. But what happens is that when running a thread, one thread might run on a specific CPU, as we discussed in the previous lesson as well. And the other thread, of course, well, it might run on a different CPU. And each CPU has its own cache memory. And what happens is that it might be that the value of C after 10 iterations is incremented only here at the CPU1 level memory and not in the main memory. So in the main memory it basically might remain 0. So that's why when printing it out from the printing thread that accessed the value, instead of printing 10 after the 10 iterations of this thread, because the change now is not in the main memory, but it's only at the buffer memory of the CPU where the thread or the incrementing thread is running, instead of seeing the value 10, you will basically print value 0. And to mitigate this, you actually use the volatile keyword. So that simply solves when you use this volatile here. So this is the kind of problem that volatile solves, because by adding volatile there, now all the changes that are done here are always also transferred to the main memory. So it cannot be anymore that a specific thread, in our case called the incrementing thread, will only make a change to its own, seen only by itself, so to its own, let's say, buffer memory of the CPU. Instead, it will actually be working with the main memory. So you are pretty sure in this case that for this C that has been declared volatile, the changes are done in the main memory. And then you will avoid these situations where a specific thread might do changes and that are not seen then by another thread, because the two threads actually use different. You mean threads are running into different machines? Is the question? No, it's just two CPUs, because now today in year 2020 we might have even a computer having 16 or 20 or 32 CPUs, isn't it? So you might have one machine with plenty CPUs. So you have this is basically in only one computer, only one program, but remember that the threads can use different CPUs of the same system. That's basically why one of the main reasons we use multi-thread architectures is to make sure we consume all the possible power when we want of a specific system. So you have one computer having multiple CPUs. In my case, to simplify the example, I have taken two of them. And then you have the situation in which, being that each CPU has its own memory, by default, the value changed is not in the main memory. And if you don't use volatile, then you might get into a situation where you have a different value used by a specific other thread when you use a shared resource. So that's basically how volatile works, and that's basically where you use volatile. But that doesn't mean that you should always use volatile, because in a lot of situations you don't care if the printed value here or if the used value here is the same one or not yet. It might be that this data consistency is not important, is not relevant for your program. I mean, more cores. Multiple cores of the processor. I think multiple cores actually means multiple central processing units, isn't it? I'm not a hardware guy, but if I didn't explain it very properly from that point of view, I think you will forgive me, because I'm a software guy, not a hardware guy. But in my mind it was that when you have multiple cores, it has actually you can have a processor with multiple central processing units. That's what I was thinking. So if I'm wrong with that, but the idea is still the same. Again, from our point of view, just take it, the idea is still the same. You can have multiple cores, multiple CPUs, tell them how you want to tell them, but the idea is the same. So you have the situation in which one thread runs on one level, the other one on another processing unit. And in this case, you might have the situation in which data is not consistent. What I wanted to tell you is that, again, the volatile keyword allows you mitigate this problem, but be sure that you have that problem, because I've seen in a lot of cases developers using volatile to solve problems that didn't exist. So you can add volatile, but if you don't have that problem, you will simply basically do more operations, and theoretically it's less performant than if you would simply leave the program without volatile. And if the data consistency, this data consistency problem doesn't exist in your specific multi-thread architecture, then don't use volatile just to put there volatile. Use it only when you have such a problem, similar to the one I have described here. If you don't have it, simply leave the shared resource without volatile, and that will be fine. And I think the last thing we need to discuss about volatile is that it doesn't solve the race condition problem. So one of the mistakes, one of the problems in understanding of volatile that I have seen is that well, this volatile would actually also solve the race condition problem. Remember, the race condition problem was the problem for which we have used synchronized in the previous lesson and today to make sure that multiple threads don't access the same shared resource. If you use volatile, you just make sure that the changes are directly transferred to the main memory. But that doesn't mean that multiple CPUs, if they are mutating, in my case I took the simplest example where one of them is only accessing. but say that both of them are changing. Okay, the same value. Well, in this case, you still didn't solve the race condition problem. So you still have multiple threads trying to access a shared resource from here and from here. And to mitigate that, you use, of course, synchronization, which can be using the synchronized keyword that we have discussed. So this is one of the solutions, but of course in the next lessons I will also teach you more ways in which you can use synchronization. But remember, just by making it volatile, you don't solve the race condition. You just make sure you use the main memory instead of making your threads individually using first of all the processor memory and then the main memory. You still have to synchronize your threads if you access for mutation from different multiple threads like we were doing in the producer consumer architecture. So you still need to use the synchronized keyword, and sometimes you use it together with volatile if you need that, but using just volatile doesn't mean you have synchronized something. There are a couple of more things I'd like to discuss about synchronized, and again, one of them is how do you use it on the method level and what does that mean. And what I want to say is that you will see people using synchronized directly on the method signature like this. Is also like a modifier, and we didn't use it like this yet, but I want to teach you how to use this one as a modifier in the method signature as well. That's one of the things I still want to discuss about synchronized. And the second one, I will use synchronized also to teach you about deadlocks, but it seems that we have already spent our time for today, so it takes me at least 20 to 30 minutes to discuss all this. So my suggestion is we leave this for the next lesson. So what we will actually do, hopefully this is clear for you, and again, remember, I will basically put everything on GitHub, and at the end of the lesson I put that on GitHub and I share the link in the specific video. So don't worry, you will have the code like for any of the other videos. I suggest you that in the next lesson we continue still with synchronized and discuss first this couple of things that we still need to discuss, like using synchronized on the method signature. You will see that there is a difference between using it on static methods and non-static methods, and that's something we need to discuss. And of course to discuss that deadlocks is not necessarily related to the synchronized keyword, is related to synchronization in general, but because we've learned the only way we've learned until now is synchronized keyword, and that's also the easiest way to explain it. I will use it to explain you how a deadlock works. And after that we will go to the executor services. So say in the next lesson we will work on the deadlock using synchronized on methods, and then we start with the executor services. So thank you very much for your questions. Thank you very much for being here with me for this live event. If you are watching the event recorded, then you can still ask questions in the comment section. And until next lesson, have a great time for study.